Okay, thank you. Yeah, I got to keep track of time. I have a lot of slides, I'm not going to lie, so I will be skipping fairly quickly through some of them. But yeah, my name's Geoff. I'm here out in Ottawa at the National Research Council with the Construction Research Center, and I'm a research officer focusing mainly on LCA. So today I'm going to give just a quick plug about the LCA Squared initiative and a quick disclaimer. Then I'm going to break the presentation down into about 5 parts. I'll talk a little bit about the current state of biocarbon accounting. And then I'll get into some important items to consider to do with biocarbon along the entire supply chain life cycle. And then I'm going to talk a little bit about biocarbon flux dynamics, taking a dynamic approach, and also albedo dynamics. And also, it's also to do with taking a more dynamic approach to estimating GWP. And then I'm going to have a quick brief note on stand level versus landscape level. So as Anthony mentioned, I'm a technical lead for this project called the Low Carbon Assets Through Lifecycle Assessment Initiative, or LCA Squared. And it's about a $6 million project over 4 years. Our main focus areas are actually developing building-related Canadian lifecycle inventory data sets, just making more comprehensive data sets that can be utilized by various tools across Canada and beyond. We're also developing a comprehensive whole building LCA guidelines. And our ultimate goal is to implement LCA into government procurement. And our main focus is starting at the federal level, but we really wanted to trickle down to all jurisdictional levels. So with that said, we have this sort of governance structure you see here with the steering committee, technical committee, secretariat, and then project teams. And this is really a good opportunity if anyone's interested in this initiative, that you can actually get involved. Just contact me and I'll sign you up to our email list and you can get involved with their technical committee if you're interested. But just a quick disclaimer. So the views and opinions expressed in this presentation are my own. They don't actually reflect official position of NRC or the Government of Canada, and they're not reflective of decisions made to date through the LCA Squared committees, nor are they a reflection of our future direction. So with that said, we do make technical decisions within our LCA Squared initiative, and they're determined through our technical committee, and it's really done through a consensus-driven approach. So starting with part 1, I wanted to start by thinking about the life cycle inventory of forestry data sets. And so one of the databases probably a lot of you are aware of is EcoInvent. And to think about what Canadian data sets are actually there's only actually 2 data sets. And they're representing softwood and hardwood forestry activities in Quebec only. And I just took a little snapshot from OpenLCA to show you the inputs and outputs. So a few things to keep in mind here is that implicitly it assumes carbon neutrality. So what that means is basically they kind of back calculated the carbon removed from the saw log coming out of the forest, and they assume that that CO2 is replenished in from the air. So that's where you see carbon dioxide in air. And it's just equivalent to the amount of carbon that's actually leaving the forest. So they're implicitly assuming carbon neutrality here. And there's actually not really any rigorous quantitative basis for this assumption. And they actually don't bring in any estimates of other greenhouse gases associated with the dynamics of the forest, like due to methane or nitrous oxide. And there's no estimates or assumptions regarding any non-renewing forest area within this landscape that it's representing. But so let's just think about where do the rules come from when in terms of ISO standards when it comes to biogenic carbon uptake and emissions when doing whole building LCA. This is the sort of authoritative ISO standard on it. And this is what it says about it. I'm not going to go into detail here. It's a lot of writing, but that's verbatim what it says. And basically what it says is that if biogenic carbon originates from a renewable resource, such as sustainably managed forests, then any biocarbon entering the product system is given a -1. And then any carbon leaving the system is giving a +1. So overall, then if it's a renewable, sustainably managed bioresource, then you essentially assume carbon neutrality. However, I didn't see any explicit mention of how to deal with biocarbon in landfill. It's not mentioned in this particular section. So it's sort of a question of how you deal with, say, carbon storage in a landfill. I mean, it does, a lot of the carbon does stay stored in the landfill for a long time, but there's no explicit, at least I couldn't find it, any explicit ruling on how to deal with it. But there is a sort of a correlation with how to deal with energy recovery from a landfill, and they say that you can mention it, consider it in Module D, which is just sort of an extra information item, but you wouldn't actually account for it in your whole building LCA. So maybe that's the best way to deal with it. So one thing I like you to think about, what is a renewable resource? Like, how would we actually quantify that? It's a resource that's grown, it's naturally replenished. That's sort of the definition that they have. It's restored, right? It's something that's going to be restored back to its former level, and I think that's a good basic definition. So this section also refers to another section on how to determine if it's sustainably managed forest. And so I just wanted to quickly go to that section here. This is the text verbatim, but let's just glean the important points. So it basically says it's a sustainably managed forest if it's certified forest, but regardless of certification. So it could be FSC, CSA, SFI, etc. Also, you can use other evidences such as national counting of greenhouse gases in terms of the forest landscape, the managed forest landscape. So if it's seen as stable or increasing in terms of net GHGs, then you could also use that as reasoning to say it's a sustainably managed forest. And so these are the types of rules that are in this ISO standard. And then if it's not certified and you don't have these other evidences, then you would posit that it's not sustainable, and you would assume that you wouldn't give it a -1 when it's coming into the system. So some important things to keep in mind is sort of the current state of the standard, you could say, state of the standards. So as we all know, Canada has a lot of managed forest highlighted here, and there's many different categories. So it's not just about forests that we actually harvest, but it could be a lot of protected forests, etc. And it could be private, long-term tenure, short-term tenure. But when it comes to reporting from the UNFCCC perspective, the accounting requirements span all managed forest types. So that's important to keep in mind. Now, and this figure basically gives you a snapshot of the maturity of our forests across Canada at the forest management unit level. So it gives us sort of some indication of the age class. We can also take some statistics to show sort of what is the age class across the ecozones, as you see here. And so this gives us sort of an indication that our managed forests with the snapshot from today would definitely be on the net, sequestering carbon on the net or GHG emissions, because basically, the majority of our age classes are in a period of their life cycle where they're on the net, they're sequestering more carbon than what's being decomposed from heterotrophic decomposition. And so, but you could argue this could be the same even if all, imagine the entire landscape age 20 or even age 15, age 30, any age above 15 or 20, you're going to see this net carbon intake. So the only time you wouldn't see it is if, at the stand level is when heterotrophic decomposition dominates. So I think that's also something to keep in mind when thinking about the net GHG over a very aggregated landscape level. And then I just wanted to quickly show, kind of highlight all of Canada's certified forests by the different certification schemes, and about 65% is certified according to these numbers anyway. And I mean, that's something really to be proud about. I think Canada is the top in the world in terms of forest certification. So that's a good thing, I think. And it ties back into the ISO rules, right? We can assume it's sustainably managed forest, and therefore it's carbon neutral. And so going into the accounting, so what we essentially do is, well, basically NRCan does it at the CFS group. They use the CBM model, carbon biomass model, which is a relatively robust carbon accounting model. And they essentially account for all of the sequestration of carbon and also the emissions of carbon across our landscape, including CH4 emissions and N2O emissions as well. And so when you look at the net accounts, you'll find that it depends how you look at it, because from the UNFCCC accounting rules, you have to include all managed forests, even if there's a natural disturbance component. And so what Werner Kurz and colleagues did in this paper is they developed the methodology to tease out or partition the fluxes between two land components. So the one that we're really anthropogenically influencing, and then the one that's been more due to natural disturbance. And so on one account, with the green dotted line on the top graph, you can see that there's been a lot of natural disturbance over the past 20, 25 years. It's fairly dominant, and so on the net, it can even be positive. And then, but if you just tease out the anthropogenic component, we're quite below, in terms of net fluxes, we're quite negative, around negative 200 million. So that's another way to look at it at the aggregate. But again, you could argue that you could come up with these numbers even if the entire landscape was, aged 20 years or 25 years, et cetera. So, one thing I question is, should this highly aggregated metric be used to decide whether our forest products are carbon neutral, or is it just too aggregated of a metric? Do we need to, to get a higher spatial and temporal resolution on this to better understand it? So here's some key questions to consider. What is a renewable resource, and how do we actually quantify it in terms of carbon? How do we quantify the renewability of our forest products? What share of forest products come from primary versus secondary forests in a given year or a given short-term time period? Do our accounts, do our modeling, does our national forest inventory accurately account for regrowth or lack thereof? Example, what percentage of harvested area actually grows back, effects due to landing and roads? In other words, how do we account for imperfect or partial renewable where significant land use change does occur or can occur? And yeah, more so, how can we explicitly model biogenic carbon GHG dynamics at adequate spatial temporal resolution? So I want to now get into the second part, which is more to do with some key accounting items along the life cycle. So I'm just going to go through a few quick ones. So here's some important biocounting items to consider. For example, some sections of a managed forest, may simply not grow back. There was a recent study from Northwest Ontario that studied 27 block cuts, where they found that on average about 14.2% of the harvest area was not renewed, and that was, that was completely due to roads and landings. Wood waste they found wood waste was the primary cause of these no-growth sections in harvest. And they found that this was sort of a continuing or persisting over time. And now I'm not saying this is true everywhere across Canada, but this was just a certain case study, which would be interesting to broaden the horizon and understand it, more across Canada, just to get a better sense of it. And so is this accounted in, standard industry whole building LCA? Well, no, not really, as I mentioned in my first slide. What about soil carbon? There's really not a lot of research on this study. There was a very extensive meta-analysis on soil carbon that looked at empirical studies to see how different treatments of a managed forest, after whether it be clear cut or whole tree forest harvest or residue spread, etc. And they sort of took an analysis on what's the effect on soil carbon, whether you lose carbon or you gain carbon. And it's not exactly definitive, and it's very, very dependent on the type of soil and whether you're talking about the mineral soil or the organic horizon. And when projected over time using chronosequence data, you see that it's very, very different data. And in general, it does replenish over a certain time horizon, and it is possible to model this, though somewhat crudely with existing models. And a lot of these models are derived based on this empirical evidence, but nevertheless is quite uncertain. And so if we can better account for soil carbon dynamics, that would be a good thing. What about forest residue management? Management like slash burning or spreading forest residues, or actually removing a significant portion of it for bioenergy. That's actually not explicitly accounted for in life cycle inventory in any typical database like ECN Vancouver. in general. So like in whole building LCA, it's not really, those dynamics aren't really looked at explicitly, especially when it comes to say slash burning, which can have significant emissions due to carbon monoxide emissions, methane, nitrous oxide, black carbon. And so when you add all these up, they can actually lead to quite a significant contribution on a per cubic meter merchantable log basis. So just comparing to that initial data set I showed for Quebec on an eco-invent, the impact to produce a cubic meter of merchantable lumber or merchantable timber saw log at the forest road is about 24 kilograms CO2 equivalent. But when you look at these effects from slash burning, they can actually dwarf it by quite a bit. So it's an interesting consideration. Of course, slash burning has a purpose. It's supposed to mitigate. It's supposed to be a fire protection approach. So, but there's key trade-offs to look at. So it's worth exploring these effects in a little bit more detail, I think. Also, comminuted wood storage management. In a large-scale operation, bioenergy plant, for example, it's not unheard of that a big pile of wood chips or sawdust will remain in a pile for several months residence time. And so there can be significant dry matter loss. One study found 2 to 4% loss per month, where there can be a certain amount of methane and nitrous oxide emissions. Typically isn't accounted for in LCA, but there has been a study, for example, here on bioethanol that found that it contributed to about a third of the impacts when considering on a per megajoule wheel to tank basis. And this is typically not accounted for in whole building LCA or in life cycle inventory. Also, landfills, we do consider it, but maybe not necessarily well enough. We don't differentiate as much as we should in terms of climate. Also, not as much in terms of fuel type, the type of biomass going to the landfill. So obviously, sawdust or some hog fuel, shredded wood would have a different decomposition rate than a very solid piece of lumber. So it'd be ideal if we can try to better differentiate this when we develop our life cycle inventory. Other I would say much more advanced considerations are stuff like, well, trees do emit volatile organic carbons. Alive trees, actually in one study, were found to be conduits for methane and even N2O emissions. These are more far off advanced scientific findings that will take a while to actually model and potentially bring in inventory. Also, trees help form clouds. So as you manage a forest, you could potentially be changing cloud formation, which has a strong effect on surface on the albedo and reflection of direct radiation. Also, effects due to climate change. How do we bring this into the equation? It's definitely not straightforward, but it's an important thing to consider in the future. How's my time? I'm probably getting close, but let's zoom into the GWP bio and thinking about biogenic carbon dynamics from a dynamic point of view. So there's been a lot of reviews done on how to deal with biogenic carbon, as you see here. I'm not going to go into any one in particular, but I just wanted to list some of these review studies in the literature. And there's been a couple of reports like omissions that exemplified and recommended the application of GWP bio, and also a guidance document from Qantas on accounting for natural climate solutions, so how to measure GHGs from land, forests, etc. And they also exemplified and recommended the application of GWP bio. So the key recommendations distilled from these reviews are essentially, carbon neutral equals climate neutral assumption is a little bit oversimplified. Dynamic approach would be better. Timing of carbon emission sinks should be accounted for in LCA. The reference situation for forest land use should be defined even from the context of attributional LCA. Even if you leave a forest alone, like the forest is one system where if you leave it alone, something happens. The same not necessarily true for an ore deposit or something. The ore doesn't keep growing. Dynamic forest models are recommended to model such dynamics. And also, like the changes in all different forest carbon stocks, such as stem wood branches and all the other pools, really need to be considered in these dynamics. And also, biomass carbon stored in products should be taken into account as well, looking at those dynamics. having the flexibility to bring it into your life cycle impact assessment. And there, even one study recommended the GWP bio approach should be applied in practice. So what is this GWP bio? Well, let's just start with what we know. CO2, whether it's from fossil fuel or biomass, well, it starts, when it's in the atmosphere, it doesn't really matter. It's still going to be having a similar warming effect, right? The atmosphere doesn't really care where it's from. And so when we think of something like sugarcane, we say, well, that's, that grows back in less than a year, so it's carbon neutral. We can say the same thing about boreal forests. It grows back over a certain rotation period, so it can be also potentially defined as carbon neutral. What about fossil fuels? Not necessarily so, because it takes potentially millions of years, so we say that's not carbon neutral. So I think it's important we need a really clear definition of what carbon neutral means. I just took a few definitions from a U.S. congressional report, and so there's very contrasting definitions of what it actually means, and I think that's something that we need to get a better understanding of. To me, carbon neutral should be a measure of the replenishment at the tree level or stand level of what we extract. It should grow back to the equivalent amount that is taken. So what's the importance of the flux dynamics? Well, you could harvest some forest and use it as bioenergy, and a lot of that CO2 is going to go up into the atmosphere, but then it takes a certain rotation period for it to grow back. So there's a little bit of a differentiation between CO2 going into the atmosphere and then it coming back into the forest resource. And so that means there's a certain residence time that the CO2 is spending in the atmosphere, and thus having potentially a warming effect, right? Similar to a fossil CO2. So there was a methodology that was developed. It was essentially derived by starting with how we actually develop GWP factors. So the way that we develop them is scientists have developed, basic impulse response functions, and these are basically decay functions of how a greenhouse gas behaves in the atmosphere. So when it comes to, say, methane or N2O, they're assumed to decay all the way down to 0, but CO2 tends to stick around in the atmosphere a lot longer. And that's actually why GWP, the reference gas to CO2, because it has if the horizon goes to infinity, you would have an infinite number. That's why we have a set time horizon of 20, 100 years, and we typically assume 100 years. So this was the basis for GWP bio. And then in this article, Cherubini and colleagues, they basically performed a mathematical convolution between the local biomass system between forest regeneration and bioenergy combustion, and basically modeled how it perturbs the global carbon cycle. And these are the impulse response functions that they develop. And as you can see, they change a lot depending on the rotation period. So how do you build these impulse response functions? Well, you need to understand the net profile over a rotation period. You also need to understand this is just some more detail on what a net ecosystem profile is. It's basically understanding the difference between net primary productivity and heterotrophic respiration, and you take the net of that. So as you can see in the beginning, in early years at a forest stand level, there'll be more emissions than it is a sink, but then the regrowth of the forest will take over, and then the net effect is regrowth, net sequestration, until overall, in this case, we're assuming what's harvested is replenished, so carbon neutrality assumption. And then also you need to consider biomass products and their profile. So like they're not going to stay in the anthroposphere forever. They might be combusted at end of life, and you also have supply chain emissions, as you produce those different products. And so that should also be considered as well. And then you can put those together, and you can come up with GWP biofactors for specific products and where it's coming from. So it's species, region specific, product specific GWP biofactors. So it does start to get more complicated. But then you can see that the GWP factor, can be positive or negative. It can have a climate cooling effect, but it can also have a warming effect. So overall, this is sort of what the equation looks like, but I don't really have time to do it. And then, so yeah, these are some examples of profiles where we consider annual crop versus a short rotation, medium rotation, long rotation for different types of products with different residence times in the anthroposphere, with this assuming that it's released as bioenergy at the end of life, or a case of carbon capture and storage. So you can consider all different kinds of combinations, and you get this kind of profile, which can then be used to derive GWP biofactors, very specific factors for products, species, region specific. But I don't really want to get into these details because I don't really have the time. I just wanted to touch on these things very quickly to give you kind of a sense of some of the research that's out there on this. So in similar effect, GWP albedo, so surface albedo dynamics can have a substantial cooling impact when a forest disturbance occurs, like a forest harvest. So thinking of the global impacts, the main drivers are the carbon cycle and then the direct solar radiation and how it reflects, and that's to do with surface albedo. So this study kind of tells it all, where there was a forest fire in Alaska, and it actually caused a net cooling effect on the average, meaning that even despite all of the emissions from the forest fire, the cooling effect, that means the reflectivity of the direct solar radiation back into the outer space had a bigger effect. It was a bigger magnitude effect, so it had a overall net cooling. And you can see the albedo differences in this picture quite evidently. Like when you harvest a forest in the wintertime, that's generally where that big difference occurs. You can see that a lot more direct solar radiation is going to reflect back into the outer space versus solar radiation hitting a fully grown forest, because it's much darker surface. And so there's been research that's looked into this, and so in the top graph you can see those differences, where the red line is the clear cut, the albedo shoots up in the winter versus an old growth jack pine forest. This is based out of Saskatchewan. So you see the big difference there in the winter months because of the snow cover. And so there's some equations to figure that out, and thinking of dynamics. Well, the albedo change is predominant in the early years, right? But then when the canopy regrows, then it essentially comes back to zero change, because it has basically the same effect as a fully grown forest, and there's no difference. But capturing those dynamic effects can play a big role, and so you can actually develop a GWP albedo factor. And so there's been studies, mostly focusing on biofuel, where you have the biogenic carbon dynamic flux, and then you combine it with surface albedo flux, and then you can have, you can look at the net effect, and you can see the blue and the green bars are kind of counteracting one another when it comes to biofuel, where the green is bio CO2 effects, and the blue is albedo. I think I'm going to skip a little bit of this because my time is kind of up, but you can also apply it to the life cycle of a glue laminated beam. If you think about it going through the life cycle, this is just a material flow analysis for a given year of biocarbon flow of wood harvest in Norway that I did a few years ago. And so, yeah, you can do the same thing with a case study. Look at the life cycle of that glue laminated beam and account for the biogenic CO2 that's emitted along the life cycle, and essentially you can account for the effects of biogenic carbon and albedo. So if I take an EPD and I superimpose the impacts of biocarbon and albedo to the EPD results here, then you can kind of get an understanding of the order of effect that GWP bio and albedo have. In the end, it would be a net negative effect because it's stored for a long time, and surface albedo has a big impact as well. Also, there's other forces to consider, like black carbon, as I mentioned a little bit earlier, and also carbon monoxide, organic carbon. These all have effects on radiative forcing. So if you bring those into the picture, the effects can really change the overall results on a this is for heating. So we're looking at stoves, old stoves and new stoves, and also district heating. And so the blue dot is the net effect. But you can see with a very old, inefficient wood stove, your impact is a lot higher than natural gas. and what the big driver there is the inefficient combustion with a lot of black carbon being affected from it. So yeah, there's all these other forcers to really consider that are in the research literature, but not really making it mainstream yet. And maybe it'll take a number of years before that happens. But this just gives you the breakdown of where the forces are occurring. You see, it's a big trade-off. There's a lot of negative forces, but also positive forces. And then you see the net effect. So yeah, I went through that pretty fast. Also considering, you can also consider old growth to manage forest dynamics. I really question, we need to come up with a good solid definition of what is carbon neutral. Where does this term come from? There's two spatial perspectives. One's the stand level, one's the landscape level. Stand level means that your carbon's replenished over the rotation period. Landscape level, you tend to think that any harvest in a given year is offset by what's regrown in a given year. But you can't really have both these perspectives simultaneously, because that would actually be double counting. Because if you're going to account for it at the stand level, you can't also use it at another stand to account for it at the landscape level like this. So it's sort of a conundrum. There's a lot of conundrums here, and a lot of trade-offs to consider. And so that was really a brief overview. In terms of next steps, I mean, where can we go from here? I think we need to take a measured response towards higher resolution accounting in general. Get better spatial temporal resolution of these dynamics of carbon, especially. Better accounting of bio-GHGs, so not just biogenic CO2, but also methane and N2O. We need more explicit quantification of net profiles representative of a given species in a region combination, and management as well. We need to start bringing this data into life cycle inventory and databases that actually get utilized by industry. So it needs to get put into these databases that are used in various tools, LCA tools. And then, yeah, we need to consider studying dynamic LCA approaches in research, and looking more into these other key sources, and test the feasibility of using these dynamic approaches in policy analysis, and even potential utilization in the industry LCA applications, even though that may take some time. It could happen eventually. So that's about all I have. Thank you very much.